Hi, my name is Eric Graeff. I'm an electrical engineering major at WSU. I did my research internship out here in Prosser, Washington, and I did my project on something called the Smart Trap. And I would like to thank Dr. Lavcott and Shrinkanth Gorthy that were my mentors here. My research project involved the codling moth, which is a pest here in Washington that destroys apple crops by laying eggs in the apples. Traditional moth traps allow farmers to control the population of moths, but they have to be checked manually. The moth does a lot of damage to apple crops, and it's estimated that growers have to spend $100 to $300 per acre annually for different kinds of integrated pest management, including how to deal with the codling moth. Without controls, it's estimated that there could be 80 to 100% crop loss in unprotected orchards. Since Washington produces over 100 million boxes of apples annually, which is between $2.5 and $3 billion, this means that even a 1% loss due to insect damage could equate to $25 to $30 million in lost revenue for growers. The Smart Trap is a solution to the problems posed by codling moths. It uses an embedded camera and computer vision to recognize moths when they're in a trap, and this Smart Trap eliminates the need for checking the trap manually. And growers can count when and how many moths are present in the trap or get stopped by the trap, and that way growers can use the data to develop a moth control plan. There were two parts that I had to understand in developing the smart trap. One of them was this machine learning and software part, and the other one was the hardware and the camera part. For the machine learning, we used Google Colab, RoboFlow, and YOLO. The hardware consisted of a camera vision module, a microcontroller that would send data to the cloud. In training the machine learning model, the first step was to get raw data images. Then I would have to annotate and label the images, which involves drawing a bounding box around each moth in each image. Then the images are split into 80-20 training and validation split. We use YOLO 8 to process the image and to train the model. And then that's ready for deployment to the field. This is an example of one of the training images. These liners get placed on the floor of the moth traps, and the camera would take a picture of this, and this is what it recognizes the moths from. In this research project, I used 300 input images. The training results came back it was very successful. It was about 99.63% of the detections that the model made were correct ones. So that means that there's very few false positives. And also the recall was good, 99.9% recall, which means very few false negatives, almost no false negatives. So for the hardware that was involved here, we had to look at different options. There's many kind of cameras on the market. We had to consider things of the camera as far as does it change out to a wide lens, because the camera has to be mounted inside a very small moth trap that has only 15 inches of distance from the ceiling to the floor of the trap. We also had to consider that the camera be very, very power efficient, because the camera needs to be in a deep sleep mode for most of the day and then come on only once during the day to take a picture. Some of the RF signals that these cameras use are Wi-Fi, LoRaWAN, and a kind of a new kind of Wi-Fi called Wi-Fi 802.11, known as hollow Wi-Fi. So we had to consider these kinds of signals and that go with these kinds of cameras. The camera that we decided to go with uses the hollow Wi-Fi. It has a better range than regular home Wi-Fi, but it had better speed throughput and data rate than the LoRaWAN signal. We conducted a range test because we wanted to check this hollow Wi-Fi signal, how far it could go, and if the vendor's claims of a full kilometer was right or if it was exaggerated. So we drove around the Prosser Research Center here, and this is a map of where we are. We placed the gateway where you see the push pin. That's the building that we worked in, and we drove around. We took signal strength notes, and we got way out to the road, and we were able to get at least one bar when we were when we were about 800 meters away. So that was pretty good range. It certainly beat Wi-Fi, but it's nowhere near as long range as LoRaWAN is. The logic for programming the hardware was pretty simple because all this camera needs to do is be asleep for most of the day. Then at 10:30 a.m. it wakes up and it syncs with the server. It takes a picture of the moth trap, and we call that the logic name we have for it is moth pick. It recognizes the moth count, so it's counting moths, and it sends that count to the cloud, and then it stores the moth pick in an array. After it does that, it just goes back to sleep for the next about 24 hours, where it just wakes up at the same time next day and does it all again. The smart trap designed in this way allows growers to be able to check on moth counts and get an accurate idea of when moths are coming without going out to the field manually. So this is a great savings for labor and time. So that's my project, and I had a really good time doing it. I learned a lot, especially about machine learning and and all kinds of programming because I'm an electrical engineering major. We learned some of that stuff, but this was pretty computer intense, and so I'm really grateful to have the opportunity to do the project. Thank you.